A spring has a mass of 1 kilogram and its spring constant is K equals to 100. The spring is released at a point 0.1 meters above its equilibrium position. Determine the type of damping that occurs for each of the following damping constants. Now the differential equation that we will use in this question is mx double prime plus beta x prime plus kx equals to 0. Equals to 0 simply because there are no external forces. Now m is 1 and k is 100. So for question 1, we can obtain our auxiliary equation by replacing m, beta and k. So we get m square plus 10m plus 100 equals to 0. Now to determine the type of damping, all we need to know is the type of roots this quadratic equation has, whether real roots, distinct roots or complex root. So what we need to find is b squared minus 4ac, which is in this case 10 squared minus 4 times 1 times 100. This is 100 minus 400. This is negative 300, which is less than 0. This means that this quadratic equation has complex roots. Complex roots would indicate that our system is underdamped. So underdamping occurs in this case. Now for question B, beta is 25 and our auxiliary equation is m squared plus 25m plus 100 equals to 0. Now b squared minus 4ac in this case is 25 squared minus 4 times 1 times 100. This is 625 minus 400, which is 225, which is of course positive, which means that the quadratic equation has distinct roots. Distinct roots indicate that our system is overdamped. So in this case, overdamping occurs. Now for question C, beta is 20 and so m squared plus 20m plus 100 is equals to 0 is the auxiliary equation, and here b squared minus 4ac is 20 squared minus 4 times 1 times 100, which is 400 minus 400, and this is 0. This means that the quadratic equation has equal roots. Equal roots indicate that the system is critically damped. So critical damping occurs in the third case.